Hi everyone, hope you're having a great day today. We're going to go to 7.4, which is over trigonometric form and complex numbers. So we're going to look at how to graph complex numbers and how we graph complex number in the complex plane. So what we've been doing up to this point is the Cartesian plane, where you have the x and y axis, and we're going to see how similar the complex plane is to the Cartesian plane. This is what we're used to, right? We have the horizontal and the vertical. Now, for the horizontal, in the complex plane, we call that the real axis, and the vertical, we call that the imaginary axis. So it's pretty much almost exactly the same. It's just that we write a little bit different, okay? So basically, in the real axis, we have number like -2, -1, 0, 1, 2, 3, and so forth. So we would graph that on the x-axis or the real axis. Now, if we have any complex numbers, so again, complex number is written as a plus bi. So normally we use z to denote a complex number. Complex numbers comes in two parts, the real part and the complex part. So the complex part have an I in it, and the definition of I is square root of -1. And you can also operate with I using the following rule. If you take I by itself, you just get -1. But if you square both sides, you're going to get -1. And then I cubed is just I squared times I. So that's just -1 times square root of -1, or just I. So you get -I. I to the fourth is I squared times I squared, or +1. And if you go to 5, 6, 7, 8, and all that, it starts back again. So I6, -1, I7, -I, I8, +1. Okay, so it's like a cycle. And there's 4 different values that it rotates around. Okay, so let's get back to this complex plane. So anytime that you have a complex number, for example, -2 minus 3i, then basically you take the 2 and the -3 as a point, and this is your real part, and this is your imaginary part. And you would just plot that point like you normally do at 2, -3, and then you would draw an arrow, and that would be your complex number, okay? All right, so how do we find the sum of two complex numbers? We just add the components together. So to add, we just add the real part together. So here we have 6 minus 2i, -4 minus 3i. If we want to find the sum, we want to add the real part together and add the imaginary part together. Okay, they are separated. So 6 plus -4 is 2, -2 plus -3, -5i. So you can see here that complex values can also be added by using vectors. And we learned how to add vectors before by taking one of the vector and moving it so that its tail is at the head of the other one. So I'm going to move -4 minus 3i over here and put its tail to the head of 6 minus 2i. And you can see the resultant force, or the resultant vector, is the value that we get after we added them. Okay? So similarly with vectors, when you are subtracting, basically the vectors just go opposite directions. So if I take 6 minus 2i and I want to subtract -4 minus 3i, what you can do is you can distribute this negative sign or minus sign, and then you just add the two vectors together. Okay, so let's look at here. We're going to add 4 plus 3i. So we're going to get 10 plus I, or 1i. So let's see what happened when we try to graph this, right? So we have 6 minus 2i, -4 minus 3i. If I want to subtract this, basically I put a negative sign there, distribute it, I get 4 plus 3i. So 4 plus 3i would be up here. You can see that it is opposite direction, same magnitude as my original vector. And then what I can do is find the resultant force by moving this to over here. And you're going to draw your resultant resultant vector from the tail of one to the head of the other. So this point right here will be the value that we found when we added, which is 10 plus I. Okay, so here's 6, 7, 8, 9, 10, and that's about 1 there. Okay. Yes.
Professor, to clarify, these coordinates 10 plus I, 2 minus 5I, they're just the coordinate point, right, in the complex plane, and they don't represent the magnitude of the vector.
Exactly. There are coordinate points. Yeah.
Okay, thank you.
So think of that as like the point of the head. If you want to find the magnitude, excuse me. If you want to find the magnitude, then you have to use the formula by using the Pythagorean theorem. So in order to find the magnitude of 2 minus 5I, let's call that vector u. So in order to find magnitude of u, you're going to take 2 square plus 5 square root. Now I'm taking the plus here because I'm actually just squaring this, so you can positive anyway. Okay. Yeah, does that answer your question? Square root 29.
Yes, thank you.
Okay, so we can see here that the vector, that we can show the magnitude of it by using r. And so we've already seen this before, that basically the vector OP have this angle that is corresponding to the positive x-axis rotating clockwise. And so anytime that I have a complex number, basically that complex number is going to be the coordinate point of the head or the terminal point that you can use in order to find out the magnitude, in order to use the theta. There is a relationship between all of these. So we call that when we deal with the unit circle as we did before, we have x and y. X correspond to cosine theta, and y correspond to sine theta. Now this was a unit circle where the radius was 1. So the radius here can be anything. So in order to do that, all we have to do is just multiply by a factor of r. So this is a scalar value, as we know. In order to multiply a scalar value, all you have to do is just distribute it. So you have any point xy is going to equals to r cosine theta, and y is equals to r sine theta for any value of point xy outside of that unit circle. Okay, and that is a relationship you see here. We have x is equals to r cosine theta, y equals r sine theta, and r is just the Pythagorean theorem. And tan here, just use SOHCAHTOA. So you can see here theta is here. So tangent is opposite over adjacent. So tan theta is equals to y over x. So there's nothing new here that you don't already know. We are just putting an I to it, so we can represent complex numbers using the complex plane, but it's basically the same Cartesian plane that you're familiar with. Okay, so here what they're doing is to give the relationship between x, y, and theta. So what we have here is r cosine theta plus I sine theta, and that is the representation of the complex number x plus yi. Okay, so you can convert from just a regular Cartesian plane by using x and y to trigonometric form. So you can see here we have trig functions, and these are equal to each other. And so in order to write this out, you can see that theta here is the same theta for both of them. So we have a shorthand notation called RCIS theta. So the R here is just this R. The C represent cosine, I sine theta. So this is just shorthand notation for R cosine theta plus I sine theta. So we use RCIS. So the only thing that changes in this form is the R and the theta. So this is the only two pieces of information that we know, since the two theta here are actually just the same theta. And that's what they're saying here. So the expression r cosine theta plus I sine theta is just shorthand notation for r cis theta. Okay, so these two are the same thing. This is just shorthand notation. Right, because the r is called the modulus. Modulus normally means the length of something. They like to use the absolute value for this because r is always going to be a positive value. Just like when we deal with a unit circle, r represents the radius, right? The radius cannot be negative. So even if you're in a different quadrant, r is always the positive one. It's your x and your y that changes the sign, okay? Okay, so sine of theta and cosine theta have a period of 2 pi or 360. Now we let the restriction be between 0 to 2 pi, basically just one cycle of it. Okay, and I think we call it, well, theta, we used to call that to call the argument of the complex number because that is the argument of the trig functions. So whenever you're writing trig function, this right here, whatever is inside it is called the argument. And this carry over for other functions as well, kind of like square root of x plus 1 minus 6. This is called the argument of square root. Okay, so now we're going to be able to convert from one form to another. So here we have trig form. We need to convert it back to rectangular form. So remember the identity that we have. X is equals to r cosine theta. Y is equals to r sine theta. R equals square root of x squared plus y squared. And tangent of theta is equals to y over x. So we're going to use one or more of these in order to express this. Okay, so the steps that I want you to do in order to do this is always try to sketch this out. Okay, I always suggest you sketch this out using what we've learned before. Okay, so I'm trying to relate this to stuff that you've learned so that you're not really learning anything. You're just basically taking prior knowledge and apply it to something else. So in this section, we are applying it to complex numbers. And we're using the unit circle with what we've learned from trig, all of the trig identities, and applying it to this. Okay? All right, so we have cosine 300. So 300 degree is in the fourth quadrant. Okay, so we know that's from here to here. That's going to be 300. Now we can draw a right triangle. Okay, so this here would be 60 degrees. All right, so now this r value, that's 2. Now I need to know x and y. Okay, well, the nice thing about this, you can use SOHCAHTOA in order to find this, but we actually have a formula for it already. So we say x is equals to 2 cosine theta. Well, what is theta? Theta here, you can use 300 or you can use 60 and then reference it back to the fourth quadrant. So cosine of 300 or cosine of 60 degree, we're using our reference angle here. Cosine of 60 degree is 1/2. So 2 times 1/2 is 1. Now, since cosine of 60 is the same thing as cosine 300, because we're in the fourth quadrant, this is just equals to positive 1. However, for the y value, we have 2 sine of 60 degree. Sine of 60 degree is equals to square root of 3 over 2. That cancel. Now, however, this is our fourth quadrant, so this needs to be negative square root of 3. So that is my y value. Okay, so in rectangular form, we have a plus bi. I'm sorry, we use x plus yi. So we found our x, we found our y. So therefore, my complex number z is equal to 1 minus I square root of 3. And you can double check this to see if this is actually in the fourth quadrant by using the point 1 negative square root of 3. That will give you this point right here. Okay, there you go.
Hey, Professor, before we continue, why does the complex plane exist? Why is it here?
Hmm. Let's see. In order to explain this, you kind of need to know to higher mathematics, because this is in higher mathematics we use I quite often, and we use the complex plane in order to convert different format of certain numbers that is much easier to deal with in complex plane. And complex plane exists is because we have to have a way to undo certain functions, because when you're trying to evaluate certain function and trying to find its inverse, it doesn't exist because it's imaginary. So we have to find a way in order to graph these kind of functions, different types of solution that deal with it. We're going to see an application of this, I think, at the end of this. So hang on to your horses, and I'll show you. Okay, so again here, I'm just showing you basically the steps. So we're going to sketch it. Right, we did that, and then we're going to find r, and then we find theta. Okay, so let's practice. All right, so write each complex number in trig form. All right, so again, we're going to sketch this. So for part A here, we have negative square root of 3 plus I. All right, so again, the point that we're going to try to plot is negative square root of 3 and positive 1. So this is going to be in quadrant 2. So negative square root of 3 is here, 1 is here. So now we can get this, which is r. So we're just going to find r is equals to square root of x squared plus y squared. Okay, so this is square root of 3 square plus 1 square. So that's 4. So we get 2. Okay, I can already know what this is because it's 1, 2 square root of 3, because that's a special triangle here. But let's go through the rest and find out what theta is equal to. Okay, so theta is equals to, we can take tangent of theta is equals to opposite over adjacent, so 1 over negative square root of 3. Now you can memorize this, or you should know this. This is 30 degrees. Now, since it's negative, it's going to give you in the fourth quadrant. So it's going to give you negative 30 degrees. Okay? Yes.
Complex plane, is it always in degrees? Do we not use radians? Okay, so it's not limited to, I can use both, got it.
Yes, yes. Yeah, so I'll show you. So we have negative 30 degree or negative pi over 6. Okay? So, but this is, theta is in the second quadrant, so we need to find out what is the value of this. So if I know that theta is going to be pi over 6, again, we try to get this to the first quadrant using the reference angle. So if that's pi over 6, then our theta is going to be 5 pi over 6. So we got r, we got theta, we can rewrite it as r cosine theta plus I sine theta, which is 2 cosine 5 pi over 6 plus I sine 5 pi over 6, or 2 r, oh wait, r is already there, r cis 5 pi over 6. So my r here is 2. And let's see the answer to that, negative 2 cis 5 pi over 6. Okay, let's do the other one. Negative 3i. Okay, so negative 3i, you see that we don't have the real part. So let's put in a 0 there, because that's a placeholder. So the point that I'm trying to look at is 0, negative 3. 0, negative 3 is down here. Well, that's easy to find r because that's just the distance from here to here. It's a straight line, so that's just 3. So we got our r is equal to 3. Now we need to get our theta. Well, we don't need to do any work here because you can just rotate from here to here. That's 270 degrees. So r CIS 270 degree. That's in degree, right? Or you can write it in radian. 3 pi over 2. And there you go, 3 CIS 270. I don't think we need to go over this one. All right, so multiplying complex numbers. So to multiply complex numbers in rectangular form, we need to FOIL. So what we're doing is we're taking multiplying here. Okay, so 1 times negative 2 square of 3, we got that. 1 times 2i, get that. I times I square root of 3 times negative 2 square of 3. Square of 3 times square of 3 is 3. Negative 2 times I, negative 2i. And the last one, we have 2i squared, square of 3. So I told you before that I squared is equal to negative 1. So this I squared here becomes negative. Now we can combine like terms. 2 of these makes negative 4i. And these two becomes negative 4 square root of 3. So to multiply complex numbers in rectangular form, all you have to do is just to FOIL. Okay, let's do a practice problem.
Could we factor out negative 4 from that last part?
No, because remember that my complex number is a plus bi form. We want to know what is the real part, what is the imaginary part. If you factor out negative 4, that does not help. Or I want to know this number need to be separate from this number.
Okay, thank you.
Yeah, so that's standard form there. All right, let's do a practice problem. Let's see. Mohammed, is your whiteboard working? All right, Mai, do B, and then Aim, you can do A. You forgot the square in the end here. This is 25i square. So how did you get 50i? Not sure how you're getting these values here. So this becomes negative 25. And then you combine that with the negative 14. And then you combine these two. Okay. So negative 25 and negative 14 is negative 39. And then negative 10 and 35 give you positive 25i. Is that okay?
Yes.
All right. Okay.
I'm not looking. Be careful. Sorry.
No problem. Okay, so multiplying complex number in trig form. All right, let's see how we do that. So we're gonna have to get the same answer here, but this looks like a lot of work, right? So let's see how they do this. So in order to multiply complex numbers in trig form, we convert it here to here. So we convert it to trig form first. So 1 plus I square root of 3. So let's draw that real quick. You can see that this is in the first quadrant. 1, this is square root of 3, so this must be 2. This is actually a 30-60 triangle, so this is 60. So we see that we have 60 degree here. And this is R for the hypotenuse. We have 2 cosine 60. Over here, we can do the same thing. Negative 2 square root of 3 and positive 2. This is negative 2 square root of 3. This is 2. So to get this one right here, that's going to equals to, is it 4? All right. So the value here, we can find out it's actually the same thing because it's just multiple of 1, 2, and square root of 3. Okay. So here, I think we got this is 30. So this here would be 150. So we got 150 and 4 here. So in order to multiply two trig values together, we multiply R together. So here's 2 and 4. We multiply these two together. And then all you have to do is just add the angles together. So see, 2 times 4 give us 8. We add 60 and 150, we get 210. That's it. Because when you do this, all you're doing is you are trying to FOIL it, and the shortcut is just to add them together. Do you know why that is? This is because that is the sum, the product rule for sine and the product rule for cosine. Okay, so this is where the sum and product rule for sine cosine comes in. Neat, huh? So therefore, in general, we have, whenever we have two complex number in trig form multiply together, multiply their modulus together, and then add the angles together. So this is very, very quick to do, and this is the benefit of doing it in trig form. Later on, you're going to see there's a few other ways that makes this very, very beneficial as well. All right, so I'll just do this one, and then I'll give you another example. When we multiply these two, here is our R value, here is our theta value. So we take 3 times 2, which is 6, CIS, 45 plus 135, so that's 180. So easy, right? So we can evaluate that because it's 6 cosine of 180 plus I sine of 180. Well, this value we can evaluate exactly to -1 and 0. So to do, and then distribute, add them together, we get -6. Okay. All right, I'm gonna give you one.
Hey, Professor, before we continue, can you explain to me, when we find -6, what is that value in terms of the complex plane? Because it really helped me when you went through the vector and you showed that, the scalar was, the dot product was a scalar and not a magnitude. So what is this like?
This is a resultant vector multiplying those two together, so you get this. So 6 is just right here, -6.
Awesome.
Remember that the real value is on the axis, whereas the complex is on the y. So any number that's on this line is going to be a real number. Any number that's anywhere else is a complex number.
Got it. And it's a resultant vector. So when you take the product of numbers, it becomes a resultant vector. Okay, I think I get it.
Mhm.
Thank you.
Okay. So let's do, give you a hard one because I'm going to give you in rectangular form. Let's not do that because then you're going to have some really nasty number. Okay, so I'll give you two. Let's see. I want to do it. Cosine 30° minus I sine 30°. Okay. Okay, Mike, go ahead and take A. All right, go ahead and aim. multiply them. My shouldn't equals to negative. Okay, you're not done. How are you, Aim?
Almost done. I'm typing it up.
Okay, very good. Wait. What is going on here? This is 195 plus 496 business.
Weren't we adding the 60 to the 35? And
Yeah.
then the 330 to the 135.
Oh no.
Yeah, I understand what was going there.
Oh, that's not supposed to be like that. I did not realize. They're supposed to both be 60. That's my mistake. So in trig form, both of these need to be the same angle. If it's not the same angle, it's not correct. Yeah, I messed up. This is supposed to be also 60.
CIS 195.
Yes, that's it. What you need to do.
Sorry, I was taking so long just to try to figure out if my math was
Yeah,
making logical sense there.
sorry about that. Okay, so now we're going to talk about quotient. How to divide complex numbers in rectangular form. Let's review that first. Okay, so let's say you have 3 minus 2i over 5 plus I. So in order to divide this, all you need to do is multiply the complex conjugate of the denominator. Okay, so multiply complex conjugate of denominator. All right, so we have 5 plus I here, so the complex conjugate of that is 5 minus I. So we're going to multiply that. Now, note the product of a complex conjugate in terms of A plus BI, A minus BI is A squared plus B squared. And I'll show you why that is. So when you multiply here, you're just going to FOIL. So you have 25 minus 5i plus 5i minus I squared. So you see these two cancel. And this one turns to a -1, but we actually added them, so we get 26. Okay. All right. So the product of a complex conjugate is always a real number. Okay, so we got here that we got rid of the imaginary part and we just have a real part, so that makes it a real number. Right, so when we multiply this in the numerator, we can FOIL. And in the denominator, we just have 26. So let's simplify this. I squared here give me -2 and 15 give me 13. These two give me also -13i over 26. But we are not done here, okay? We need to rewrite this in the form of a plus bi, so we can identify what is a and what is b. So we need to divide this and separate it out. So 13 over 26, that's 1/2, minus 1/2 I. So my a here is 1/2, my b here is -1/2. And there we go. We just divided a complex number.
Hey, Professor, when we're writing in the rectangular form, do we want to keep the 1/2 separate of the I, so it's better to write 1/2 I rather
Yes.
than...
Why I did it that way.
Yes, sir.
Let's try this example. Go ahead and divide that and see what you get. You guys
Not
get
quite
negative
yet.
8i? Okay, so the result we got after we divide that complex, those two complex numbers, is negative 1/2 I. Did you guys get that? Okay.
12 minus 8. How was that 16 in the denominator? 12 minus 4i, isn't that 4i squared?
Yeah, so I squared is negative 1, so negative 4 times negative 1 is plus 4. So
Oh, I subtracted, okay.
yeah, I squared is equals to a negative 1.
Okay, so
So we can see in notice that when I convert it to trig form here, we get from 2 to 4 by dividing, right, 1/2. We have 2 divided by 4, we got 1/2. To get from 60, instead of dividing, we are subtracting. So 60 minus 150 give us negative 90. So negative 1/2 I is the same thing as 1/2 cosine of negative 90 plus I sine negative 90, which is the same thing as 270. So therefore, in order to divide, our quotient theorem is basically just subtraction of the angle, whereas multiplication, we add them and we multiply our modulus. Okay, so let's
Professor,
find.
isn't this kind of similar to what we learned in logarithms, kind of?
Yes, log of a times b, that is log of a plus log of b. And when we have log a divided by b, we have log a minus log b. So kind of similar, but not exactly facting the argument. Okay. All right, so let's review. All right, so to multiply complex number in trig form or polar form, so we have a plus bi times c plus di. So in trig form, we have r1 cis theta 1 times r2 cis theta 2. To do this, we would multiply r1 times r2 cis theta 1 plus theta 2. And if I want to divide, a plus bi divided by c plus so here we just divide, and CIS we are going to subtract theta 1 minus theta 2. Okay. All right, so to do this problem, very easy. All we have to do is divide 10 divided by 5. We're going to subtract negative 60 minus 150. We have negative 210 degrees. So we need to find a coterminal angle that is the same thing as negative 210. Well, negative 210 is actually in the second degree, right here. So if we add the 180 right here, we have 30 degrees. So this would be 150 degrees. Our answer is 210, negative 210, or the same thing as 2 CS 150 degree. And so if you put that back into rectangular form, all you have to do is evaluate what is cosine of negative 210 or cosine of 150, and that is the same thing as cosine of 30 degree in the second quadrant, so therefore it is negative square root over 2, or sine of 30 degree, which is positive in the second quadrant, you get 1/2. Distribute your r, and we get this. Easy peasy. Questions? Well, that's it for today. Any questions?
Our test, right? I know that for this test, we're going to have 4 weeks worth of material to cover rather than the 3 weeks in the previous 2 tests. And then I know that in the past lectures, you state that there's going to be a lot of sketching of vectors, especially the hard ones requiring us to understand bearings and be able to sketch it out correctly. With that being said, will there be the same amount of questions on test 4, 30 multiple choice questions, or will it be less because we're covering more material?
We'll still be hovering around 30 questions. Yeah.
Okay. And then for test 4, are we going to cover, I haven't seen the syllabus in a little while, sir, so I apologize, but is it going to be all of chapter 11, sir?
We're not doing, I'm sorry, test 3 will be all of chapter 11, so 11.1 to 11.7. Right now we're doing, I forgot which one this is.
This is
4, yeah. Questions to cover.
Okay, so,
and then we'll have 9 sections, all of them. But the chapter 12 is very easy. That's actually in college algebra, so it will be a review. The exam 4 will have a lot of sketching, though, sketching and graphing.
Yes, sir. And then I'm just curious, I haven't looked forward yet in the next 3 sections. Kind of trigonometric identities in the complex plane, sir?
See. I don't know.
Yeah. Okay. So for this upcoming test, right, like that we need to memorize, that we need to understand, like how we did the unit circles and the IDs in the previous 2 tests.
So understand, know how to apply law of sine, law of cosine, when to use it. So what we just learned, I think in 11.3, I would suggest you review that because that's probably the hardest section, because that deals with the airplane problems, the ground speed and the airspeed, how to sketch the correct graph so that you know where the drift angle is going. I think that will be the most difficult. Everything else here is just formulas. You have formulas to find the product of something. You have the formula to convert from trig form to rectangular form. All of those are using some kind of formulas. You don't have to really understand much. But 11.3 really requires you to understand everything and be able to know how to sketch it very carefully.
Got it. What's the performance of our last test look like? Did we meet your expectations as a class from the last test?
It was better. Let me see. It was definitely not where I wanted it to be, but I'm not really too surprised because that's actually kind of normal. I did have, let me see here. I will probably end up curving a lot of these anyway. But let's see, I have a lot of zeros because people are not taking the exams, sadly. 1, 2, 3, 4, 5, 6. Okay, so I have 20 people in the class, 10 of them did not take the test. So, which is kind of depressing. So, but again, they didn't take the first test either, so I don't know if they have any reason for that. But I've sent emails to them, reminding them and asking them why they did not take it, and they have their own personal reason, but still, that's pretty bad. Like an 80% failure rate for this class. I don't see how you're gonna pass if you miss 2 exams. So I've encouraged them to drop and try again, or if you want to stay until the drop date and then you can drop out. You can feel free to attend lectures, I guess, but yeah, it's not gonna do you any benefit if you're gonna stay and get an F.
Yes, sir. I have some personal questions which I would prefer to speak privately, so I can
Yeah.
wait until after the class is ended, sir.
Yeah. Comment, do you have any questions? No? Fine, if not, I will see you guys next week. Ending the recording now.